We've talked about things that are ionically bonded, covalently bonded, and metallically bonded. In this unit, we will go into more detail with those substances that are covalently bonded. Typically, if something's covalently bonded, it's a nonmetal bonded to another nonmetal, and we call the result a molecule. When we look at molecules, molecules get a lot more complex than substances that are ionically bonded or metallically bonded. And so we represent these molecules by drawing what's called a Lewis structure. A Lewis structure is just a dot diagram put together. So for example, if I were to draw the molecule CO2, I could first draw the dot diagram from carbon. Carbon has 4 valence electrons, so you need to include those valence electrons in their dot diagram. When we have a dot diagram of a single element, the order is important. Remember, you put 2 electrons in on one side, and then you put 1 electron on each of the other 3 sides before you repeat the pattern and make them share. So carbon, I put 2 electrons on one side, and then I put 1 on the other side. So this is when the element is all by itself. When you put it together in these Lewis structures, it's okay to move your dots around. So when I draw CO2, carbon always has 4 bonds. So I'm just going to slide that 1 dot over to the other side, and then I'm going to connect my oxygens. So oxygens have 6 valence electrons. When you look at their dot diagram, we get this. So oxygen has, with the 6 valence electrons, it will bond right where those single bonds are. So when I go to put it together, I get something like this right in the middle with the graphic. So instead of dots, X's are used for carbon. So you see that we have a few electrons in between the carbon and the oxygen. And these electrons, they represent a bond. When we draw a bond, instead of drawing all those dots, because it can be cumbersome, we can use a line. And for every line, that equals 2 electrons. Typically, it's 1 from each of the elements. So when I draw that CO2, instead of drawing all those dots, I can just draw the lines in between the carbon and the oxygen. CO2 is doubly bonded, so we have a double bond between the carbon and oxygen on either side. Electrons determine the shape of the molecule. When you look at how we put these Lewis structures together, it's how many bonds are there and how many unbonded pairs that are there that determine the shape. Electrons will repel each other in the bond. So why did I draw in CO2 the double bond far away from each other? How come I didn't draw it close to each other like this? And that's because these electrons will repel. And so they want to get far away from each other as possible. And this is called VSEPR theory, VSEPR theory, which stands for valence shell electron pair repulsion theory. It just means that the electrons in the bond repel each other. So instead of them being all cramped up in the CO2 molecule like I've drawn here, you are going to see it far away from each other right here. So you can see that those bonds will repel each other, and I will get a molecule that is straight in shape instead of all crinkled up. This next molecule is water, H2O, and water on its oxygen has 2 unbonded pairs, and the unbonded pairs have even more repulsive power than just the bonds. So what we have is these unbonded pairs will push the bonds between the oxygen and the hydrogen even closer to each other. And this last molecule, this is ammonia. We have 1 unbonded pair, sometimes it's called a lone pair, and it will repel those 3 bonds closer together. So this creates 3D structure. The rest of this slide shows that uh, electrons in the bond, you have 2 electrons for a single line. If you have a double line, then that means you should have 4 electrons, and a triple line, you will have 6 electrons, or 3 pairs. You should have a handout that has these Lewis structure rules. It might be in your packet or it might be separate, but you shouldn't have to take notes on this. This should be given to you. this is just general rules for how to put these Lewis structures together. It's very helpful to have a model kit, so that should be provided for you, that you can go and look and put these atoms together and figure out what shapes their molecules will be. There's kind of two ways to draw these Lewis structures, and I will teach you both ways. The first way is to count the valence electrons, and then you will connect the atoms just with a line representing a bond. And remember, every time you draw a line connecting two atoms, that represents two electrons. Typically, the atom that comes first, that will be the center atom. So you're going to start there and then connect all the other atoms to that one. The atoms that are usually on the end are hydrogen, oxygen, or halogens. Remember, the halogen family is right next to the noble gas family, and they have 7 valence electrons. So there are exceptions all over the place with these Lewis structures, but generally you're going to make every atom have an octet or have a full 8 valence electrons, just like a noble gas. So your noble gases, they are stable because they have these 8 valence electrons. We have bonding between nonmetals. They will share electrons to be able to get these 8 electrons. So it's called the octet rule. There are exceptions all over the place though. For example, hydrogen is a very, very small atom, and when it bonds, it only has one electron to contribute to the shared bond. So when you draw these Lewis structures, you're going to end up with just a bond with the hydrogen. And you shouldn't have any dots ever on a hydrogen. Let's look at oxygen. So when you look at oxygen, its dot diagram, you will have 6 valence electrons, and you should always pair them up, and oxygen will bond right where those single electrons are. And halogens. So for example, fluorine. Fluorine has 7 valence electrons. So when it goes to bond, it's going to bond right where it has its little single one. And so all halogens will look like this. They'll have 3 pairs around them or 6 electrons. Always pair them up, and then you'll have a dash representing the bond. Anytime you have carbon, carbon will always have 4 bonds around it. It can double and triple bond. But you'll also see single bonds, so you should always have 4 lines coming away from the carbon, and very rarely will you ever have an electron on it. Probably you won't see that in my class. You'll always just draw the 4 bonds around the carbon. I've already mentioned this rule right here with hydrogen, so let's move on. If there are too few electrons to form octets, then you'll form double or triple bonds. And if you're building with a model kit, you should fill in all the holes for that are on the little wooden ball that's representing the atom. If you have some holes that are empty, then that tells you that you're going to have to make a double or a triple bond. Some of your small atoms having 8 electrons around them would just overwhelm them. Hydrogen is one of them. It just needs 2 electrons. So by the time you draw that little bond, which represents 2 electrons, you're done. Beryllium is also very small. It just needs 4 electrons, and boron and aluminum, they're in the same family. They need 6. So just as a little information about isomers, isomers are when you have the same formula but can bond it together differently. So for example, this right here is C4H10, and there's 2 different ways that I can bond this. The first one is a butane, the second one is a propane. You don't need to know how to name these, you just need to know how to string the carbons together, surround them by 4 bonds, connect the hydrogens, and then you should be able to rearrange it by cutting off or removing the last carbon and putting on a middle carbon. And that will give you 2 different structures that are 2 completely different molecules because they're bonded in a different order. So let's look at some examples of these before you do your lab. And so that you know how to do your homework too for drawing these Lewis structures. So there's a family associated with each shape. Let's start with the linear shape. In the linear shape, we have the alkaline earth metal family. So some of the smaller alkaline earth metal families, when they bond with nonmetals, they actually form more of a covalent bond than they do an ionic bond. And our example formula, this would be beryllium fluoride. I told you I was going to teach you two different ways to do these Lewis structures. And so one way is to count valence electrons. So looking at your periodic table, we find that beryllium has 2 valence electrons, and the fluorines, each of them have 7. So the total number of valence electrons would be 16 valence electrons. So this means when we draw the Lewis structure, we want to include all of those valence electrons. Beryllium is listed first, so that is going to be our center atom, and we're going to connect the 2 fluorines. And VSEPR theory says those bonds will be far away from each other, so I want to draw them far away from each other. And remember, every line that we draw, that represents 2 electrons. So I have 2 bonds, so that would be 4 electrons that I've used. I need to draw 6 more. And so those 6 are going to go around our halogen fluorine. So we'll pair them up. You should have 6 of them on each of them. And again, put them in pairs. And we have our beryllium fluoride. So the bond angle, that would be from bond to bond. And this is linear, so it has a 180-degree bond angle. So this is one way to do it, by doing the skeletal structure. Another way that I like to do this is to just draw the dot diagram and try to figure out how it goes together. So for this one, we're going to start off with our beryllium. Beryllium has 2 valence electrons. And remember, when we bond, we can move things around so that they're across from each other like this. And then I'm going to draw each of my fluorines. The fluorines, they have 7 valence electrons. And then I'm going to draw a bond between the fluorine and the beryllium, and just kind of scribble in and color in a bond from each of the beryllium and the fluorine. Either way, I get the same answer whether I count valence electrons or I draw original dot diagrams and put them together. You're still going to get this linear molecule. Next, we come to the shape trigonal planar. The family that makes this is the boron family. And we will be drawing boron trifluoride. And when we look at the valence electrons, boron has 3 valence electrons. The halogens have 7. And we multiply by 3, so we have a total of 24 valence electrons. So boron goes in the middle, and we connect these 3 fluorines, and so we have this shape, trigonal planar. And the bond angle between here and here, it's a circle cut into three pieces, so that would be 120 degrees. And last, we have our shape tetrahedral. Last, at least on this slide, there's a total of 5 that you need to know. The family that forms tetrahedral is the carbon family. And I'm going to show you carbon tetrafluoride. When we look at the valence electrons, we see that we have 4 valence electrons, and then we have 7 valence electrons times 4 is 28. Plus that 4, we have 32 valence electrons. Draw your carbon in the middle. Remember, carbon always has 4 bonds to it, so draw those out. And then we'll draw our fluorine. And we need to put dots on our fluorine. When we look at this shape, we find that it is a 3D shape. And so it's not a 90-degree angle. It's not a circle cut into 4 pieces. Instead, it's a 3D shape. And the bond angle is 109.5. So it's a little bit closer than 180, and it's a little bit further than 90 degrees. So at 109.5 degrees, these 4 bonds will be the furthest away from each other as possible. And they make a shape called a tetrahedron, and so that's why this is called tetrahedral. Let's look at 2 more shapes. These 2 shapes are a variation of the tetrahedral. The trigonal pyramidal, the family that makes this shape is the nitrogen family. And we are going to look at the formula NCl3. So nitrogen trichloride, let's add up the valence electrons. So we have 5 valence electrons, and then our halogen has 21 total. So we should have 26 electrons. So drawing this structure, if we look at nitrogen, nitrogen has 5 valence electrons. And so I'm going to connect bonds right where those single electrons are. And this is where I'm going to put my chlorines. And we're going to draw the 6 pairs all the way around. And when we look at and add up how many electrons we drew, we have 24 in those 3 chlorines. 8 times 3 is 24. And then we have 2 more in that unbonded pair. When we look at the bond angle, that unbonded pair, it will push the bonds closer together. So it's going to be even closer than 109.5. The bond angle is going to be 107 degrees. Okay. With that nitrogen trichloride, the unbonded pair actually, because it doesn't have 2 atoms to go in between, it actually spreads way far out and that pushes those chlorines together. But we don't draw it that way with that big circle, but that is what's going on. Let's do one more family shape. So this is the bent shape, and the family that does this is oxygen family. And the formula for this, I'm just going to show you water. When you look at the valence electrons, oxygen has 6 valence electrons, hydrogen has 1, and there's 2 of them. So that adds up to 8 valence electrons we need to draw. On this one, oxygen is going to be in the middle because hydrogen can only single bond. And oxygen, it has 6 valence electrons. So it looks like this, kind of on its side. And I'm going to put a bond right there and a bond right there and connect that hydrogen to it. And so I have 2 bonded pairs and 2 unbonded pairs. And those unbonded pairs, or those 2 lone pairs, they have a bond angle even closer than the trigonal pyramidal, and it's 104.5. So again, if you don't have electrons going back and forth between 2 atoms being shared, there are lone pairs or unbonded pairs. They will repel those bonds even more, and so the bonds will be closer to each other. So these are the shapes that you should draw in your lab. So you should look at the formula, you should figure out what the structure is going to look like, and draw each of these. Here's another graphic that just shows you what I drew. So it has some other examples that shows you each of the different shapes. And here's a chart that also shows you the shapes, how many bonded pairs they have, and what their angles are.